Hello, everybody. I am back from, yeah, you guessed it, from the shirt, New York City. So it's the first time I went there. Absolutely gorgeous. The weather was absolutely terrible. It rained so hard, harder than I've ever seen before on the Saturday and the Sunday that I went. But luckily, on the Monday, it was absolutely beautiful. Saw the Statue of Liberty on a cruise and also went up the World Trade Building, the tallest building in North America now. Super stunning. So if you guys ever get the opportunity to do that, it was absolutely gorgeous, aside from the crappy weather. Now, you don't care about that. If you did, I appreciate it. But for the rest of you, this video is about demystifying deep learning, so how neural networks work. A lot of my videos, I go very into theory about the different components that are going on and really break down step by step so you understand every single piece. That is not the purpose of this video. It is one of my overview videos where I'm going to talk about the different components, what those are, so that when you're ready, you can go in and pick out those pieces when you can, or watch full tutorials that are really going to break down each of the pieces. And this way, you know the pieces that are involved here. I'm going to break down and list 10 different components. There's going to be some overlap. But here we go. So number one is the basics of neural network and deep learning. So basically just the overall idea of what we're saying here. Neural networks are a machine learning algorithm. Some people call them a data structure because they are kind of a thing, but they're more of an algorithm. And again, what an algorithm means is just kind of a set of rules. It's something where you do something with data to get some sort of a result. Now, what we mean with neural networks and machine learning in general is generally our algorithm is learning from data. Okay, so you could have a neural network, and don't worry about the structure for now, but it's just this black box, picture just this black box that's able to kind of figure out patterns in data. Now, since it's able to figure out patterns in data, you might be able to build a supervised learning algorithm or neural network, which is able to maybe figure out the difference between a cat and a dog in an image. So it can look at those images. It's seen, say you've shown it, say 100,000 images of cats and dogs before, and it's able to figure out, hey, this new one I haven't seen before, this new one is a dog, and this new one is a cat. It may not be perfectly correct because it's learning from data. It's probabilistic. It's taking a guess, but it's a statistical algorithm as well. Statistics plays a key role. And so these algorithms can learn from data and try to make a result. And they're used for so many different things. I'll get into it a little bit more later of what they can be used for. But they can be recommending things for, say, Netflix, recommending what movie to watch. For Google, they can use it to kind of help predict what the user is typing. So you've seen it like they kind of know what you're typing. You can use machine learning for that. Same thing after you've searched your result on Google, they can kind of use machine learning to help give you back a result that they think is helpful. Not really going to get into how they use that, and that space is getting very complicated now with the addition of ChatGPT and Bard. But yeah, there's a lot going on with deep learning. Okay, so that's basically the overall idea there. Now, not too much information, but just an overview. Now, number two is the structure and components of a neural network. Now, the structure and component of a neural network is kind of hard to discuss because there's a lot of different things that you can do. There's many different architectures. And so I'm going to kind of merge this with number three here, which is common architectures for deep learning, such as convolutional neural networks and recurrent neural networks. Okay, so the structure and component of a neural network is generally the list of rules that you're going to apply to a piece of data to get a result. Okay, so a neural network, you're going to feed it a piece of data. Okay, so say one image. What is an image? Well, to you, it might just look like something pretty because you're used to it being visualized because that's what images are good for. However, mathematically, an image, you can actually break it apart. It is just a set of numbers. It is, if it's an RGB image, it's 3 channels, so red, green, and blue. You can basically picture a bunch of red pixels stacked on top of a bunch of green pixels, stacked on top of a bunch of blue pixels. You merge that together into a 2D result, and you have an image. Okay, that's what it is mathematically. And so the structure and components of a neural network, well, you would want, if you were using a neural network to do something with images, you would want it to have the structure that takes in an image. Okay, and same thing if you had text. If you're making something like ChatGPT, your neural network would need to have the structure where it can take in and appropriately handle text. Okay, which is just a sequence of words. Words are kind of complicated in machine learning. Again, words are actually numbers as well. Sometimes they're completely separate tokens. Sometimes they're treated as vectors. It depends on the situation. But yeah, basically the structure and components of your neural network, common architectures, basically it's just this whole thing where whatever piece of data you're using, whatever problem you're trying to solve, you would want to make a neural network that can take that as input. You do appropriate transformations to it, like various additions, multiplications, subtractions, whatever it may be. And then eventually you get it to a output that you would want. And the output is probably the most important part. Ignoring all the other layers in a neural network, basically, you would want to make sure that your output of the neural network is built so that it's solving the problem that you're trying to solve. And so, again, if you had a cat and dog classifier, we'll call it, basically you are trying to predict the probability that an image is either a cat or a dog. Well, you would want to make sure your output can actually handle that. And so there's basically two ways you could do that. You could either make the output end in one number, which is it's called a sigmoid I'm about to use the word in a moment, activation. So there's many activation functions, which is just another kind of transformation. We'll talk about that in a bit. But there's two ways to do this. You could end it in a sigmoid function, which is just one number that represents the probability of either one of the two, either cat or dog. Or you could end it in two nodes, so two values. And so one would be the probability of cat, the other would probably be probability of dog. But you don't really need that because you can just get the other one from one minus the other one. That's how probability distributions work. Okay, so that's basically the structure, components, and various architectures for deep learning. We've got recurrent neural networks. We've got transformers are very, very important right now. And just plain vanilla networks are the ones you're going to hear most about. And I think I said convolutional neural networks before are something that are good for dealing with images. Not really going to get into the details there. Okay, now I think we're at 4, is the backpropagation algorithm for updating weights in a neural network. Now, basically, how do these neural networks train? So I told you sometimes that it's seen like many, many images, and sometimes I've told you it's just seeing one image. Well, a neural network needs to be trained, okay? It needs to learn from data so that then later it can perform inference, so that you give it some new example it hasn't seen before, and you're actually using it to do the task that you want, like predict the probability of a cat or dog in some new image. So to enable for these algorithms to be able to do this well, they have to be trained, and so they have to be fed lots of data. Now, the most well-known algorithm for doing this, most widely used, it's kind of tweaked in various ways depending on where you go, but it's called backpropagation. And it's called backpropagation because when you're doing inference, when you're actually using the network, you do a forward pass, you send the data through the network to get your output. But then backpropagation is about actually learning from that particular example that you saw. And it turns out that you can kind of go backwards through the network to calculate the gradient with respect to a loss function. I know that's very complicated, and this is getting into the nitty-gritty. I don't want to do that. But basically, there's this backpropagation algorithm that allows you to learn from the examples that you saw, that the network saw, so that it's able to adjust its parameters, okay? And so basically, a neural network is a bunch of transformations, okay? It takes a piece of data, and then it does a bunch of transformations in a row. It does transformations based off of a set of parameters, which is just a bunch of numbers. You might also have heard them called weights and biases. There's actually a site called Weights and Biases because of that. So basically, when it's learning through backpropagation, it's taking in this piece of data. It does a forward pass through the network to get your output, and then you go back through the network to do your backpropagation. What it's actually doing is kind of slightly tweaking its inner parameters, its inner values, its inner weights and biases, so that it can slightly better understand the pattern of the data. That's basically what it does. Okay, so then the next idea is strategies for avoiding overfitting and improving model generalization. Now, underfitting and overfitting is not a wildly complex topic, although it is a discussion of its own. Basically, there's two problems that any statistical model has, which is one, it can underfit, which means the model is not complicated enough or good enough at the task to solve the problem at hand, to be able to capture the pattern in the data. The other problem is overfitting, which means the training, the piece of training information that you sent it, if you gave the model 100,000 images, it's so good at understanding those images. It's perfectly good at that. It's basically memorized what those 100,000 images are so that it can perfectly fit the data. That itself, that might sound really good, but it's actually not good because, or at least it's potentially not good. Because what you want your model to be good at is usually not fitting the training set of data. You would want it to do good in the future because you're training a model so that it actually does something. You want to make sure that it's able to do something good. And so if you are, you have say 10 new images that you need the model to classify, cats or dogs, you'd want to make sure that it can do that. You're trying to train the model on some set of data so that it can do good in the future, not so that it can memorize what it's already seen. So that's the problem of overfitting. If it's basically memorized the training set of information, the piece of training data that or the many examples of training data that you've used to train the model. So yeah, you want to avoid underfitting and overfitting. I don't want to talk too much about the strategies to do that. In a neural network, there is something called, dropout. So basically, there's a probability of making all the values in a layer 0. You may or may not want to use that. And there's also regularization, which basically means you are kind of forcing the model's parameters to not have as much flexibility as they normally would. All of these sort of generalization, overfitting techniques, they're almost always about kind of limiting the model in some way, forcing it to be not as flexible as it could be so that it's not able to memorize the training set. Okay, so those are basically those ideas there. Now we have how to tune hyperparameters for a neural network. So basically, hyperparameters are given this name because they're not really like the parameters that I discussed earlier. They're not like I'm not talking about the weights and biases in this neural network. I'm talking about hyperparameters. Okay, what the heck is that? Well, basically, you know how I said earlier how through backpropagation you can train your neural network by slightly adjusting those weights and biases, those parameters of the model through data that the model is seeing. Now, basically, you can ask the question, how much do you want the model to change? Okay, I was saying it changes by a little bit. What's a little bit? Well, this all breaks down into complex mathematics, but there's something called the learning rate, where basically how fast or slow do you want to learn? The slower you make the model learn, you're much more likely moving in a better direction. However, it's slow, like it's physically slow because the computer is doing this task, and so you're only moving it a little bit. So you want to move as quickly as you can while still going the right direction. Because if you try to learn super fast, if you picture this massive learning rate, well, this is a statistical optimization. It's not like you can just immediately optimize this thing. You have to go tiny little bits in the right direction because you're learning from data, generally small amounts of data, like 1 image or 4 images or 8 images at a time. And I'm always saying images, by the way. This works for text or whatever you want to be. It's just people commonly explain it with images. So there's the learning rate, which is basically how fast do you want to learn. There's something I basically just said, which is the batch size. Your GPU or TPU, which is probably training your models, can only physically fit however many images at a time. Remember, images are just a bunch of numbers, sometimes a lot of numbers. So your GPU can only physically take a certain amount of images at a time. That's called that would be called the maximum batch size, but the batch size as a hyperparameter is basically a whole number that you would say like, you should feed the model 1 image at a time, 2 images at a time, or again, feed the GPU 4 images at a time. It's the same thing if I'm saying feed the model 4 images or feed the GPU 4 images because the model is generally stored on the GPU. And you'll see that in PyTorch that you literally move the model to the GPU. Okay, so those are some hyperparameters. There's some other ones as well. And I just kind of gave a hint into the next topic, which is popular deep learning frameworks and libraries, such as TensorFlow and PyTorch. So basically, there's coding this stuff is very, very easy. And especially with ChatGPT right now, you can get it to do, like, it knows TensorFlow and PyTorch very, very well. Which is wonderful. Of course, the frameworks are changing. The research is changing every single day. But the frameworks themselves are relatively stagnant now. Like you can, I mean, they're changing, but like if you learn them, you're not really going to have to keep up every single day with how the frameworks are changing. So there's the two main ones, which is TensorFlow and PyTorch. PyTorch was made by Meta's team, and TensorFlow was made by Google's team. Go figure. It's the two of the big AI companies. Google's probably the biggest. Meta is definitely up there, maybe second. They've got Jan LeCun, which is a phenomenal speaker about this stuff. And basically, there's these two libraries that are almost always used in Python. Occasionally, some people do some stuff in JavaScript, and maybe you might go down the C++ route, but probably not. There's really no point of doing that because they've written these frameworks in such a way that if you write code in Python, it is very, very fast to execute. So TensorFlow and PyTorch are going to allow you to structure the pipeline of your data. So again, we've got images. What images? Where are they coming from? Is this a live resource? Like, are they actually being streamed from somewhere else? That part you probably wouldn't use TensorFlow for, but it would kind of take in that pipeline anyway. What kind of model are you creating? What do you want to do to the data before? Something called pre-processing. What do you want to do to the data or model after, called post-processing? What model do you want to use? What architecture? What hyperparameters do you want to set? TensorFlow and PyTorch, you can write some code to make and train a model and use a model. Okay, so two more. The applications of deep learning in various fields, such as image recognition and natural language processing. So basically, deep learning is used for all sorts of stuff right now. In fact, people don't even know if it's a good choice to be used or not. It's taken over stuff like forecasting, where you're trying to predict models in the future, where there's so much theory about like linear regression or linear forecasting, and then you'll see massive tutorials from people like me that show that you can use deep learning, like LSTM networks are a type of recurrent neural network that are great at understanding this time sequence stuff like forecasting. And so maybe they're good at that, maybe they're not. It's hard to tell. But they are definitely good at stuff like Tesla's supervised learning algorithms, where they're trying to predict all the stuff that it's around. So object detection is that main function. Basically, you can picture, say, 60 times a second or whatever frame rate you want. You're kind of updating the model's or the car's awareness of all the stuff that it's around. So there's a person here with, say, 95% confidence. It's never perfectly confident. It's still a statistical thing, but it's saying there's a person here. There's a stoplight over here. What color is it? Is it green, red, or yellow? Is all the cars that are around me? What time of day is it? Like, is it dark out right now? Is it easy to see? There's a lot of stuff that you can build into these systems, and they can be through post-processing. You can kind of make, say, a car do certain things based off of the things that it sees. Okay, and obviously I really have to say ChatGPT, of course, is machine learning or generative AI. It's there's some fascinating stuff going on with natural language processing right now, if you still want to call it that. I feel like that term is almost dying compared to just generative AI because of so many advances and stuff like DALL-E as well, like the image generation. It's turned into like just prompt engineering, which, by the way, I'm so done with the term prompt engineering. It's very frustrating to me. It's not hard to prompt these things. If you take a course in it, you still might learn something about how it works. I'm not saying it's a complete waste of time, but please don't go around saying how good you are at prompt engineering. It's just very silly, but it can be an important skill nonetheless, and people actually care for it. aside from that mini rant, yes, there's deep learning applications in all this stuff. Pretty much all the stuff that normal machine learning can be used for, deep learning and neural networks can be used for as well. And finally, future directions and challenges in deep learning research. Now, it is really a very interesting question because it looks like artificial intelligence is very heavily like automating itself, basically, because any sort of data scientist job now, you can tell ChatGPT to do it and it will do it well. Of course, that doesn't remove the need for the human job. I'm not saying a computer can immediately take that over, but a challenge in deep learning research is definitely what it is automating and what the jobs are turning into, because to be honest, nobody really knows. We do know that you're going to need experts in the field at every step of the way. Even if computers are very heavily automating a ton of this stuff, like even website creation up until the design points, like it's even just, it can make a website for you, do whatever backend, possibly machine learning functionality that you want, and then give you a great result. No matter to what level the automation is, you're still going to need people that can understand that well, because why would you just want a computer to completely take over everything? You're building user experiences, you're building applications for people, and so of course you would want people to give feedback on what's being done. So genuinely the challenge is we don't really know where the deep learning research is headed. It's a very exciting and scary world right now, but trust me, there has never been a better time to learn machine learning. It's great to be up to date in this field, to even just talk to your friends. And while everyone's talking about ChatGPT, you can say, yeah, well, it's basically a supervised learning system. It's a large language model, which is just a type of transformer model. And OpenAI has also used this reinforcement learning from human feedback thing, where they've been shown the output of a large language model like GPT-4, and many humans have said, no, I don't like this response. This is how you could do better. And then they've created a chatbot basically out of that, which is fascinating. So even just to understand this stuff and try to follow vaguely what these things are doing, rather than it just being a complete black box of you hearing the terms like, oh yeah, it's not sentient. It sort of is sentient, not going to lie. It's very, very good. It understands stuff well. It doesn't technically feel things because we know it's just kind of electrical pulses in a computer. Nonetheless, it's very, very good. Slight tangent, I suppose, but of course, it's an exciting thing to talk about right now. I hope that helped you understand a little bit about the broad overview of neural networks, many of the ideas that are going on. I think there's never been a better time to learn about neural networks. And if this excited you to kind of go and jump in to the pieces and fill in the gaps where I left, there's many gaps of things that I said. There's it's just that there's an infinitely many gaps. You can go and look and explore any single piece here. And in terms of the kind of overall bullet points here, yeah, go into each of those pieces. Not necessarily in order or even just searching them out, but just make sure that you've kind of checked off all these things that I've said. And I hope you have a great day. Hope you enjoyed the video. Subscribe if you're not already. Drop a like on the video if you have not. And thanks. Bye-bye. See you guys later.